ओके, लेट्स बिगिन फाइबर ऑप्टिक कम्युनिकेशन सिस्टम। तो इस लेक्चर में हम देखेंगे कि ऑप्टिकल कम्युनिकेशन सिस्टम के जो कंपोनेंट्स हैं उसका जो इंट्रोडक्टरी पार्ट है वो हम इस लेक्चर में देखेंगे। तो एनी ऑप्टिकल कम्युनिकेशन सिस्टम कंटेन्स थ्री थिंग्स। वन इज़ ऑप्टिकल सोर्स, another one is optical fiber, and last one is optical detector. In the case of optical communication system, you play with optical signal. So actually you play with optical signal means you play in optical domain. At left hand side you can see there is an optical source. What is the function of this optical source? This optical source basically converts electrical signal into the form of optical signal. At left hand side, in this side you play with electrical signal, that's why we say it's a electrical domain. So please remember what is electrical domain and what is optical domain. So what is the function of optical source? It converts electrical signal to optical signal. Means we can say it is converting one form of the energy to another form of the energy. A device which converts one form of the energy to another form of the energy is known as transducer. Means you can say your optical source is behaving like a transducer. Okay, so what are the example of optical sources? LED and laser are the best example of optical source. Okay, second thing, you can see in this side there is a optical signal and there is a device which converts the optical signal to electrical signal. Again we can say it has converted one form of the energy to another form of the energy. Then we can say this device is acting as a transducer, and this device is known as optical detector. And optical detector, what is the function of optical detector? It converts photon to electron. But in the case of optical signal, if you want to launch a light from optical source to optical fiber, you need another component that is known as coupler. So coupler is the device which couples the light from the optical source to optical fiber. So let's talk about the optical fiber. You can see the geometry of the optical fiber, and in this optical fiber there are two regions. One is core region, another one is cladding region. So on the basis of the size of the core, we classify the optical fiber into two parts. One is single mode fiber, another one is multi-mode fiber. In the case of single mode fiber, you will see the diameter of the core is less than 10 micrometer, and in the case of multi-mode fiber it is greater than 10 micrometer. So look at here. First see the definition of refractive index. What is refractive index? It is the ratio of velocity of light in free space to velocity of light in medium. This is the basic definition of the refractive index. Okay, let's see. When I move in the radial direction, then you can see there is a refractive index in the core region, that is N1, and refractive index in cladding region is N2. You can see the refractive index in the core region is higher than refractive index in the cladding region. Okay, when you move in the along the radius of the optical fiber, you see there is a larger refractive index in core region and less refractive index in the cladding region. And this graph is known as refractive index profile, and this type of profile is known as step index profile. And it is not necessary that you have always a step index refractive index profile. You may have triangular profile. What is the meaning of this triangular profile? Means in the core region, the refractive index will vary in triangular fashion. In this case, refractive index will vary in parabolic fashion. So these three are the example of the refractive index profile. So let's talk about optical source. In this lecture I will briefly explain all the components of the optical communication system. So what is optical source? Actually, optical source is a device which converts the electrical signal to optical signal. Electrical signal means injection of current. Current is related with electron. This device has been converted electron to photon, and this type of shape is known as Gaussian shape. I'll discuss later. But what are the example of optical source? LED and laser are the best example of the optical source, which is made by the semiconductor material. But this semiconductor material must be a direct bandgap semiconductor material. So what is direct bandgap semiconductor material? In any energy band diagram, you see two types of band. One is conduction band and another one is valence band. You can see the minima of conduction band and maxima of valence band. Minima of conduction band and maxima of valence band are in same line, then we say it's a direct bandgap semiconductor. What is the condition? Minima of conduction band and maxima of valence band must be in same line, then we say it's a direct bandgap semiconductor. Okay, suppose that there is a electron and there is a hole, and electron meet with hole, then this process is called recombination. And what you want, actually you want the generation of photon. Suppose that electron meet with hole and it produces photon, so such type of recombination is known as radiative recombination. Okay, let's talk about this Gaussian pulse. Suppose that there is a LED or laser and it is producing a light beam, and we get a spot here. It is the spot of beam. At the center you can see the intensity is maximum, but when you move in radial direction, then intensity is reducing. Let's draw this profile. At the center, intensity is maximum. When you move in radial direction, intensity is decreasing. Intensity is decreasing in this fashion, or you get such kind of profile, and this profile is known as Gaussian profile. And what is the equation of this Gaussian profile? That is P naught into e power minus 2t square by tau naught square. What is the advantage of this Gaussian pulse? And in Gaussian pulse, if you take the Fourier transform of this Gaussian pulse, then you will get Gaussian pulse in the frequency domain. This is time domain, this is frequency domain. Why do we say it's a time domain? Because graph is plotted with respect to the time. And if you take the Fourier transform, then you will get the same profile and in the frequency domain. Okay, suppose that the at this point, at the center, at this point the power is 1. Okay, in these two points the power is half. In these 2 points power is half. Let's draw the projection. On the horizontal axis. You get a width, but you have got this width when power becomes half. You get this width when power becomes half. That's why we say it's a full width. This is full width. When full width you have got after when your power becomes half. That's why we say it's a full width half maximum. Okay, so briefly I have discussed about the optical source. Let's talk about the optical fiber. This is your optical fiber, and optical fiber is nothing but it's a transmission medium. So in the case of RF propagation, free space is the medium. So this is your optical fiber, and I have drawn here only the core region. And what is the refractive index of the core region? That is N1. And you have launched the pulse of this pulse. at the end you have seen the intensity of this pulse has been reduced, means the amplitude of the signal has been reduced, means this phenomena is known as attenuation, means reduction in amplitude or reduction in power is known as attenuation. Okay, what are the root cause of the attenuation in the case of optical fiber? Absorption, scattering, reflection. These are the root cause of the attenuation in the optical fiber. In this world, every medium offers two things. One is attenuation and another one is distortion. Suppose that you have launched this pulse, at the output end you get such kind of pulse. Can you say both pulses are same? Answer is no. You can say this pulse has been broadened, or you can say the shape of the pulse has been changed. And change in shape is known as distortion, distortion. And in the case of optical fiber, we say it's a dispersion, and there are different type of dispersion: intermodal, intramodal, and polarization dispersion. And in the case of optical fiber, we say it's a broadening of the pulse. So please remember, in the optical fiber there are two things, attenuation and dispersion will always present. Attenuation means reduction in amplitude, dispersion means change in shape. Let's talk about the optical detector. Optical detector is a device which converts photon to electron. It's a reverse bias. What are the example of optical detector? Optical detector, APD detector, pin detector. These are the two best example of optical detector which converts photon to electron, or you can say converts the optical signal to electrical signal. So this is generally we use direct band gap semiconductor in this case also. Okay, let's see. This is the spectrum of the optical fiber, and this was the early fiber. Early fiber means in old days we use such kind of fiber. First you see this characteristic. This characteristic is plotted between attenuation versus wavelength. Means at this wavelength, at 850 nanometer attenuation is high. At 1300 nanometer attenuation is low, and 1550 nanometer attenuation is too low. This is the spectrum of the optical fiber. Means we should use 1550 nanometer wavelength, because at this wavelength your optical fiber is exhibiting or showing minimum attenuation, and you want actually the minimum attenuation in every medium. Okay, so this characteristic I will discuss again later. First you again, one thing that you have to remember always, that is 800 nanometer, this is known as 800 nanometer band, this is 1300 nanometer band, this is 1550 nanometer band. I will discuss this characteristic again in the case of optical fiber. So what are the basic component of the optical fiber? The basic component of the optical fibers are optical source, optical fiber, and optical detector. Recall what was electrical domain, what was optical domain. Core and cladding exist in the optical fiber, refractive index profile, as well as optical source. In the case of optical source, we use semiconductor material. It must be direct band gap semiconductor. This type of recombination is known as radiative recombination. It produces the light, and the shape of this pulse is known as Gaussian pulse. What is full width, half maximum, what is attenuation, what is dispersion, I have explained briefly in this lecture. And what is the function of optical detector? It converts photon to electron. This characteristic is very, very important, because we say it's a spectrum of the optical fiber. What is 800 nanometer band, 1330 nanometer band, 1550 nanometer band. In this band we get minimum attenuation, so I should use this wavelength rather than this and this. So this is all about the introductory part of the optical fiber communication system. If you like this lecture, then please like, subscribe and share it. Thank you very much.